Hello, in this video we will study how to find eigenvalues and eigenvectors. Suppose you are given a matrix L, then we will say that a matrix X is called the eigenvector and the number lambda is called the eigenvalue corresponding to this matrix L, such that if and only if Lx is equal to lambda x. So, and here x must be non-zero. What does that mean? You are given a matrix L, okay? You will say that the new matrix X is called the eigenvector and a matrix lambda is called the eigenvalue if this equation satisfies. This means Lx, if Lx is equal to lambda x, then such non-zero matrix X is called the eigenvector, and this number is called eigenvalue. Okay, so the question is, how can we find this matrix X and this scalar lambda for a given matrix L? Okay, so here is the procedure. Suppose you are given a matrix L, then since we have to find a non-zero vector X and a scalar lambda, so what we will do, we will write this equation and try to find X and lambda, okay? Because we have to find X and lambda such that those X and lambda satisfy this equation. So we will write this equation for X and lambda, then from that equation we will find both of X and lambda, okay? Okay, so we will write this equation and from here we will do some operations and find the value of X and lambda. Look, what we have to do, the first step is shift this value here, this matrix here. You will get Lx minus lambda x is equal to 0. Okay, look, this is the matrix, so there is no problem. Here we have a problem. Here this is the number and this is the matrix. So I want to write here two matrices also, because here you have two matrices. What will I do? Lx minus lambda is a number, so there is no problem. I can write the matrix I times x is equal to 0 because I is identity matrix. And we know identity matrix times matrix X is equal to X. So there is no problem. So I can write this thing in this way. So once I have written this thing in this way, then what can I do? I can take this X common from both of the matrices, from here and from here. So I will have L minus lambda times I times X is equal to 0. Here the important thing is that you cannot write this X to the left of each of the term, because X is to the right of each of the term. Therefore, I have written here X to the right and this thing to the left. Okay, once you have written this equation, and we know this is the matrix equation, this is called the homogeneous system of equation of in terms of matrices. So this is one matrix, this is another matrix, and this is 0. So this case Ax is equal to 0. You know this system has solution, if a non-zero solution, if and only if the determinant of A is 0, okay? Because we need those x which are not equal to 0, okay? We have to find non-zero vector. So in order to find non-zero vector, so we need the determinant of this thing to be 0. Okay, so I will write for non-zero matrix X, we should put the determinant of this matrix is equal to 0. Okay, we will put the determinant of this, determinant of L minus lambda I is equal to 0. So this equation is very important because this could be used to find the value of lambda. Okay, so from this equation we will always find the value of lambda. This is important equation. We will use it when we will be doing an example. Okay, so from this equation we can always find the value of lambda. Okay, so once we have found the value of lambda, your next target is find the value of x, because we have to find in our task is we are given L, we have to find lambda and x. Okay, so if we find these two values, that means we are done. Since we have found the value of lambda from this determinant, then we have to find the value of x. How can we find the value of x? Since lambda could be found from here, once you find lambda, you will put this lambda in this equation. In this equation, okay? If you call this equation equation number 2 and you call this equation as equation number 1, from here, if you put the lambda, the number lambda into this equation number 1, so from equation number 1 you get determinant of equation number 1 is L times lambda I times x is equal to 0. So I have written down the equation number 1. So here you will put the matrix L because L will be given and lambda is found from equation number 2. You will put that lambda from 2 here, then you can easily find the value of x. So these are the two processes, two procedures which are used to find the value of lambda and the value of x. Okay, so equation number 2 will be used to find the value of lambda and equation number 3 will be used to find the value of x. So from these two equations, we can always find eigenvalue and eigenvector for every given matrix L. So this is the whole procedure. Now we will do an example. If we look at the previous example, which I have done in the previous video, I gave you a Leslie matrix, and the Leslie matrix we have studied that from P20 it is, we have L of P19 which is equal to lambda times P20. L of P20 is equal to lambda times P20. And lambda was 1.25 over there. So I will write lambda is equal to 1.25. And from now on, L of, for example, P21 is equal to 1.25 times P21. So this is what we had in the previous video. Okay, so that means I have explained in the previous video that this 1.25 was the eigenvalue. So our proposed eigenvalue here is 1.25. So this is the matrix. So I will find the eigenvalue of this matrix by using this technique. By using equation number 2 and equation number 3. So this is our target, to find the eigenvalue and the eigenvector. Okay, so this is our target. We have to find the eigenvalue and the eigenvector. So in order to find the eigenvalue, we will write this equation number 2, which is determinant of lambda minus L minus lambda I equals 0. So I have written down the determinant of L minus lambda I equals 0. Then what will I do? I will put this matrix L, since this matrix L is here, and lambda is not given, we have to find it. But we know what is identity matrix. So what will I do? I will put this lambda as it is here, and the determinant of this this L minus lambda times identity matrix. Since this is 3 by 3 matrix, so this identity is also 3 by 3. Okay, always this identity depends upon this matrix. Okay, so I have placed the values of L and I. Since lambda is unknown, so I have written it as it is. The determinant of this whole thing is equal to 0. Now what will I do? I will write this matrix as it is, and then I multiply this lambda inside. Whenever you multiply this lambda inside, here you will have lambda, and here you have 0, 0. Here you have 0, here you have lambda, here you have 0. Okay, here 0, here 0, and here lambda, because when you multiply lambda inside, here everything will you everywhere in the main diagonal you will have lambda, and elsewhere you will have 0. Okay, so I have multiplied this lambda inside. I got here lambda in the main diagonal, and elsewhere I got 0. Now what will I do? I will subtract this matrix and this matrix. What will I do? This it means I'll write this thing minus this thing, and 2 minus 0, this minus 0, and blah blah blah. Okay, so I have written down this subtraction here. Okay, so once I have written down, then I will simplify these values. After simplification, I will get this thing. So I got the determinant of this whole matrix is equal to 0. In other words, the determinant can be written as, instead of this sign, you can write the straight lines here and here. That means the determinant of the matrix is 0. So since I have to find the value of lambda, how can I do that? The only possibility is to expand this determinant along any row or any column. If I expand it along the first row, in the first row you know that there is no 0, so it's not good. You can do that, but if you want to reduce your calculations, you have to choose a row or the column which has less number of zeros. You can choose row 2 or row 3 because both of them have 1 0 entry. So I will do expand this determinant along the last row. Along the last row, the first entry is 0, so I have no need to write the first entry, plus the second entry is minus 1 to the power 3 plus 2 times this number is 0.25 times the determinant of the submatrix obtained by deleting this row and this column. I'll have this thing. I'll write this thing here. Okay, so I have written down the determinant of this thing. Now it's the turn of this. So I will write negative 1 to the power 3 plus 3. Okay, look. Why I have written here negative 1 to the power 3 plus 2? Because this element is in the third row and the second column. Okay, so for this I have written down negative 1 to the power 3 plus 3 because it's in the third row and the third column. Okay, times minus lambda times the determinant of the submatrix obtained by deleting this and deleting this. So I have written down this submatrix over here. Okay, so and over here actually I have made correction here because when you delete this and you delete this, you get this thing and this thing. Okay, so I have written down those things over here. Okay, so now if I simplify this value, because this is minus 1 to the power 5, 5 is odd number, so I will write minus 0.25, and then the determinant of this is the product of these two. Since the product of these two is 0, because 0 times anything is 0, minus the product of these two. Okay, then I will write plus minus 1 to the power 3 plus 3 is 6, which is even number. So minus 1 to the power even number is plus, but this is minus lambda. So I will write minus lambda times the product of these two, which is negative lambda times 0.25 minus lambda. Okay, minus the product of these two, which is 2 times 0.50. 2 times 0.50 equals to 0. If you multiply this thing inside, you will have plus 0.3125. Okay, now if you multiply this minus lambda here with minus lambda, you will get plus lambda square times this whole number, 0.25 minus lambda. If you multiply this minus lambda with this term, because I have distributed this minus lambda with this term and this minus lambda with this term. So if you multiply this minus lambda with this term, so minus both of minus will kill each other. You will get plus lambda times 2 times 0.5 is 1. You have 0. Okay. Then if you simplify this thing, 0.3125 plus, if you multiply this lambda square inside, you will get 0.25 lambda square minus lambda cube, because lambda square times lambda is lambda cube, plus lambda equals 0. If you rearrange these things, you will get negative lambda cube plus 0.25 lambda square plus lambda plus 0.3125. Why I have rearranged? Because I needed the maximum power here, and then one less power here and one less power here, and the constant term here. Now, since this is the cubic equation, in order to solve the cubic equation, I have told you in the previous couple of videos, maybe in some previous video, you have to guess the first root. I mean, the first root could be 0, 1, minus 1, 2, minus 2. If this doesn't work inside here, then you will add some number here or some number here. I mean, you could do that 0, 0.51, minus 0.5, minus 1, and then you can check over these values or you can check over these values. Okay, so we will start checking from these values here. So first of all, we will check 0 will work or not. If you put 0 here, 0 plus 0 plus 0 plus 0.3125 is equal to 0, it will not work, because this thing is 0.3125 and this thing is 0, so they are not equal. So if I put 0.5 here, then what will I get? Okay, so in this cubic equation, if I put lambda is equal to minus 0.5 in here, then if you will check through the calculator, that this will be 0. So if this thing is 0, that means lambda is equal to minus 0.5 will work. So if this will work, then you can do the synthetic division. What's the synthetic division? In the synthetic division, we have to write the coefficient of lambda cube, which is minus 1 here. So I will write minus 1 here. Then I'll write the coefficient of lambda square, which is 0.25. So I'll write 0.25 here. Then I'll write the coefficient of lambda, which is plus 1. So I'll write plus 1 here. Then the constant 0.3125. So I'll write 0.3125 here. Okay. Since lambda is equal to minus 0.5 is the solution, so I will write minus 0.5. Okay. So then I will shift this number as it is down. I'll get minus 1. If I multiply this minus 1 with minus 0.5, I will get 0.5 plus 0.5 I will write here. Now if I add these two things, I mean plus 0.50 or plus 0.5, whatever you want, it doesn't matter. If you add these two things, you will get 0.75. If you multiply 0.75 with negative 0.5, you will get minus 0.375, 0.375. Now if I subtract this number from 1, I will get 0.625. Okay, now what will I do? I'll multiply this number with this number. I will get negative 0.3125. Now if I add these two things, you will get 0. Okay, so now what you will do, since the original equation was lambda cube, lambda square, lambda and constant, since you have taken one root away, now this equation will be lambda square. This will be the 1 power less. So I will write negative lambda square plus 0.75 times lambda plus this constant 0.625 is equal to 0. Since this is the quadratic equation, okay, since the general form of the quadratic equation is a lambda square plus b lambda plus c equals 0. So if I compare these values, I will get a is equal to minus 1 because the coefficient of lambda square is minus 1 here, but here the coefficient of lambda square is a, so a is minus 1. Similarly, b is equal to 0.75 and c is equal to 0.625. Now by using quadratic formula, we have minus b plus minus b square minus 4ac over 2a. What's minus b? Minus b means minus 0.75 plus minus 0.75 square minus 4 times a times 0.625 over 2 times minus 1. If I do these calculations, okay, look, what will I do? Once I will write with plus, and because you have plus and minus, once I will write with plus and once I will write with minus. So look, I have written once in with plus and one with minus. Okay, if you do the calculations from the calculator, from here you will get 1.25. And if you do calculations from here, you will get negative 0.5. So the possible values of lambda are negative 0.5, negative 0.5, and 1.25. 1.25 of this, negative 0.5 is this, and 1 negative 0.5 is from here. So you have two negative 0.5 and one's 1.25. Since we are talking about the population and the population cannot be negative, it can always be positive. So my valid value of lambda will be plus 1.25. So lambda will be 1.25. Okay, so come back to the example. When I gave you the example, then I told you that in the previous video I have explained when we do this Leslie matrix and we perform just matrix multiplication and find the population after some number of years, then we come to know that from year 20 and from now on, from year 20 and later on, we will notice that it is the factor of 1.25. So our expected or proposed eigenvalue was 1.25, and since from these all of the calculations we end up with the point 1.25, so that means it's nicer thing, it's the same thing. Now if you want to find the corresponding eigenvectors, what you will do, you will use equation number 3 from above. So from here you will use equation number 3 and you will put the value of lambda and the value of L in this equation number 3. You can easily find the eigenvalue, eigenvector x. So I will write L minus lambda times x is 0. Since L minus lambda I is already found in the previous step, because in the previous step we found the determinant of L minus lambda I, but before finding the determinant, this whole thing inside is just L minus lambda I, okay? Because this is the determinant of L minus lambda I. So here inside this whole thing is L minus lambda I. So I will use this thing because I have already found it. So I have written down this L minus lambda I, and then I'll write x here. So I will write here x. X can be x1, x2, x3 is equal to 0. 0 means the column vector 0, 0 and 0. Now if I simplify these values, these things, I will multiply this matrix, this row with this column. What will I get? I will get this times x1 and this times x2, this times x3. So I have written down this first row, and then I'll go to the second row because there is no other column. I'll multiply this with this one. I'll get 0.5 times x1 minus lambda times x2. 0.5 times x1 minus lambda times x2, and then I multiply the last row with these columns. I'll get 0.25 times x2 minus lambda times x3. 0.25 times x2 minus lambda times x3 equals 0, 0 and 0. Okay, now if I compare these values, the first value is equal to 0 and the second value is equal to 0 and the third value is also equal to 0. Okay, but here you can check, we have involved lambda. Since lambda is already found, our lambda is 1.25, so I can put here lambda in place of lambda 1.25. So I have placed 1.25 in place of lambda, and then if I simplify these values, I will get this thing will be minus 1. So I will write minus 1 here. So no need to write minus 1. I will just write minus here. Now if you want to solve this system, what you can do this right in this in the augmented matrix form. So the coefficient matrix from the first row will be minus 1, 2 and 2.5. And then the coefficient matrix from the second row will be 0.5 minus 1.25, and the coefficient of x3 here is 0. So 0.5, minus 1.25 and 0. And then coefficient from the last row is 0, 0.25 minus 1.25. So 0, 0.25 minus 1.25. And the last thing here, everything is equal to 0, 0, 0. So I will write here 0, 0, 0. Then I'll convert this matrix into row reduced echelon form, and then we can find the values of x and y and z. So my first step is to make here 1. Since here we have minus 1, what will I do? I'll multiply the first row with minus 1. If I multiply r1 with minus 1, then I'll get this plus, this minus, and 0 doesn't matter. Okay, once I have done with this minus, this 1, then I will make here 0. How can I make here 0? Look at here. Since this number is 0.5, which is in R2, minus what I have to write here so that I can use this 1 is to make it 0. So here I have to write obviously 0.5 0.5 times 1, because 0.5 minus 0.5 times 1 is 0. So this is the only possibility. So I will write 0.5, and this 1 is coming from R1. So I will write this operation. I will make this operation. Since I have to perform this operation, what will I do? In the row 2, what will I do? I will do R2 minus, so R2 I have written minus 0.5 times, so everywhere I will write minus 0.5 times something, minus 0.5 times something. What's that something? That something is R1. So here I will write the value of R1, which is 1 here, and here it is minus 2, and here it is minus 2.5, and here it is 0. So I will write here 0. Okay. Now if I simplify these values, I will get this row. Okay. The other rows remains the same. Now I have to make here 1. How can I make here 1? If I divide this whole row by negative 0.25, I can get 1 here. So what I have to do here, I have to divide by negative 0.25. Here I have to divide negative 0.25. If I do this, here I will get 1, and here it is 0. Here it is 0, so no need to do that. But here I will get negative 5. Okay. So I got 1 and negative 5. What I have done, I have divided R2 by negative 0.25. Now I have to make this 0, and I have to make this 0. So I will perform two operations, the one in here and the one in here. Okay, how can I make this 0? Since this is 0.25 minus what number times 1? So the obvious answer is 0.25, because this 0.25 is coming from R3, and this 1 is coming from R2, because from here I took this one, and this number is as it is 0.25. So this is the operation which I'll perform to make here 0. Okay. Now in order to make here 0, what will I do? Since this is minus 2, this is since negative number, so I will write plus some number times this 1. So the obvious answer is 2. Since this minus 2 is coming from R1 and this 1 is coming from R2. So this is the operation which I'll perform to make here 0. Okay. So in R1, what I have to do, R1 plus 2R2, what will I do? R1 plus 2R2, R2 is 0, okay? So here I will write R1 plus 2R2 is 1 here. And here R1 plus 2 times R2 is 5, because R2 is 5. R1 plus 2 times 0, okay? And in the last row, what will I do? R3 minus 0.25 times R2. So here I have 0 minus 0.25 times R2. R2 is 0 here, so I will write 0 here. So 0.25, okay, minus R3 minus 0.25 times minus 0.25 times R2 is 1. Here I will write 1. And again R3 minus 0.25 times. So I will write here minus 0.25 times R2 is minus 5. So here I will write minus 5. Here I will again write minus 0.25 times 0. So this number will again remain 0, because everything times 0 is 0. If I simplify this whole matrix, I'll get, so after simplification, here I will get 0. Now you can check this is the reduced HLN form, row reduced HLN form, because here the pivot entry, here there is no pivot entry in this column. Here you have pivot entry and here you have pivot entry. And since we know the column which has no pivot entry corresponds to free variable. This corresponds to x1, this corresponds to x2, this corresponds to x3. So here x3 is free variable, okay? So I will write, since there is no pivot entry in the row 3, so x3 is free. So I can assume x3 is a number t from the set of real line. So I will assume that x3 is free number from the real line. Okay, so if x3 is any free real number, then what is the row 2? Row 2 says x2 minus 5x3 is equal to 0, because this one means x2, this one means x3. So 1 times x2 minus 5 times x3 is equal to 0. Okay, since x3 is t, so I can put here t. So x2 minus 5t equals 0. So x2 is equal to 5t. Now, in order to find x1, I will compare the values from R1. R1 says 1 times x1 minus 12.5 times x3 is equal to 0, because this is 0. So no need to read this. x1 minus 12.5 times x3 equals 0. So from R1, 1 times x1 minus 12.5 times x3 is 0. Since x3 is again t, so I will write t here. x1 minus 12.5t equals 0. In other words, x1 is 12.5t. So the solution is, so the eigenvector is x1, x2, x3, which is, what is x1? x1 is 12.5t and x2 is 5t and x3 is t. So if you take common t from all of these, you will have 12.5 and 5 and 1. So you will say that this is your eigenvector. So eigenvector is because all of the eigenvectors are the multiple of this vector. So this is the basic eigenvector. Okay, so corresponding to lambda is equal to 1.25, the eigenvector x is equal to this. So this is the eigenvector and this is the eigenvalue corresponding to the Leslie matrix. So this is the whole procedure to find the eigenvalues and the eigenvectors.